welcome to my channel, and today this video will cover gear ratios in vehicles, what they are, what they do, why we have them. So as you can see on the screen here, we have some images of different types of gears, different sizes, all meshing together in different ways. If you look in the middle here, we have two gears, and one of them is called a driver and one of them is called the driven. So essentially the driver is where the input torque is coming in, and the driven is where the torque is going out. In the next image to the right here, we also have another gear in the middle called an idler gear. These are commonly found when we want to achieve reverse. So in the middle diagram you can see with the arrows that the driver and the driven turn in opposite directions, whereas in this diagram the driver and the driven turn in the same directions. So it's a way of reversing the direction of the driven gear. Like I said, that will be found in reverse gear usually. So why is this driver and driven gear important? So a gear ratio is there as to do two things: to reduce or increase the output speed, and to reduce or increase the output torque. So that is the twisting force. So in this case here, these gears look the same size. So we could say that the driver gear, if that was turning at 100 RPM, then the driven gear would be turning at 100 RPM. We could also say that if there is 100 Newton meters of torque going through the driver gear, then there will be 100 Newton meters of torque going out of the driven gear. So that would be what we call a 1-to-1 ratio. So if I put this like that, that is how we would state that there. Okay, so let's look at a couple of other examples if I can draw them out here. So if I draw a gear there, and then I draw another gear there. So let's say this large gear is 2 times the size of the small gear, and the small gear has 10 teeth on it, and the large gear has 20 teeth on it. And what we'll have here is the input torque. So this is coming from the engine, and this can be our output. So this will be going out to the wheels or the final drive depending on the design. So just by looking at that, you can probably say there's a 2-to-1 ratio going on there, and that's quite simple. But there is actually a calculation that we can use, and that calculation is driven divided by the driver. That equals our gear ratio, which I will call GR. So in this case, the driven gear is the large one and the driver gear is the small one. So if I do 20 divided by 10, quite simply, that equals 2. Okay, so essentially I've got a 2 times ratio. Sometimes for simplicity, people write it like this, 2-to-1. But effectively, what that means is that the small gear is going twice the speed of a large gear. So for every 1 revolution of the gear with 10 teeth, this is going to do half a revolution. So this is going to be going slower. Now if I had another number in here, I'll just change colours for the numbers. So let's put a really simple number in here of 100 RPM. Okay, our output speed is going to be half, so we can simply use this number here, and we can do 100 RPM divided by 2, and that is going to give us 50 RPM. And that's as simple as it is. So even if we get more complex numbers, different teeth numbers, different ratios that aren't whole numbers, such as 2.8, 2.7, 3.2, whatever it is. The basic maths is exactly the same. It might be, if you're not very good at maths, you might need to use a calculator for some of this, but the format is the same. So whenever you're working these out, you just need to follow this same format. If I had a different colour here, I could also say that I've got 100 Newton meters of torque coming in, but this time we don't divide. What this gear reduction does, is it actually increases the torque. So if you think about in a push bike, if you're riding that and you go into an easier gear that's going to give you more torque, so you can pull a wheelie or go up a steep hill, your output speed's not going to be as fast. You have to pedal faster to get that output speed. So what we're going to do with this number is simply multiply it by the gear ratio. So I'll do 100 Newton meters multiplied by 2, and that's going to give me 200 Newton meters. Okay, and that's it. So we can see that this simple gear ratio set here has doubled the torque and halved the speed. Now, if you're thinking further ahead here, you might be thinking, what happens if we work the other way around and the 20 was the input and the 10 was the output? It will just switch these. So we would have a greater output speed and we would have a lower torque. And we can work these out with different examples. So I'm going to work through some of these examples next. Okay, so we've seen how basic gear ratios work and why we use them. But the example I've just shown was quite basic. And actually, if we look at the picture here, this is more like what a manual gearbox looks like. So this is your typical front-wheel drive gearbox in most vehicles. So what happens here, I can show you with my pointer, we have the input shaft, which is where our clutch is. This turns with the torque from the engine, moves inside there. We have our gear selectors, and whichever gear we select then meshes with another gear down here, comes out this way, and then meshes with another gear which goes into our final drive and differential assembly. A rear wheel drive is similar, but the differential assembly is usually separate from the gearbox. We call this a compound gear set. That means it isn't going just through 2 gears, it's going through usually 4 in this case. Now, that's quite complicated there. If you just want to know about gear ratios, we don't really want to know the ins and outs of this in this particular video. So what I'll do over here, I'll draw a basic example of what's going on. So I have my input shaft. I then have a gear there, which then meshes with another gear here, which then travels along here. So this is the path of the torque. Sorry about this, the lines aren't very straight. And I'm going to put a little gear here and a really big gear here. And then that is our output. So output there and input here. Now I'll just throw in some numbers here. Now bear in mind this isn't to scale. So on this gear here we'll have 40 teeth. On this gear here we will have 80 teeth. On this gear here we'll have 20 teeth. And on this gear here we'll have 100 teeth. So I'm using bigger numbers, but it doesn't matter, the maths is still the same. If you can multiply and divide, you can do these calculations. So what we're going to do with these, so it's still the same, we're still going to use our driven divided by our driver gear. That is our formula there. So let's have a look what's going on. So I want to know what the gear ratio is from the input to the output, and we can express that as one gear ratio in total, and I'll show you how we do that down here. So let's break it up. Let's do this first section first. So the driven gear is this one here with 8 teeth, and the driver gear is 40. So if we write it down, we shouldn't go wrong. But even if we do, we can try and find out where we went wrong. So the driven gear, in fact, I don't want to use that colour there. The driven gear has 8 teeth divided by the driver, 40 teeth. Okay, and I'm going to have a look at this side here. Now, the torque is now travelling along this shaft here to the gear with 20 teeth. That now becomes, in this part of the diagram, the driver gear, and that is a driven gear. So the driven gear has 100 teeth, and it's divided by the driver, which is 20. And all we have to do in these situations is multiply these gear ratios together. Okay, so underneath, I'll do a different colour so we can see what's going on. 80 divided by 40 is, gear ratio 2. So 40 goes into 80 twice. And I multiply that by 100 divided by 20. So 20 goes into 100 5 times. And that is going to equal 10. Okay. So that's a 10 to 1. So that means that the output is going 10 times slower than the input, which is quite a lot, but what that gives us the advantage of is an increase in torque by 10 times. So again, with this example, if I put some numbers in, let's use the easy numbers again. We'll have 100 RPM, 100 Newton meters. Okay, so let's work this out here. So 100 RPM divided by that ratio of 10 equals 10 RPM. Now obviously a real car is going to be doing probably at least 1000 RPM when you're setting off. And over here I'll do 100 Newton meters multiplied by that 10. And that's going to give me 1000 Newton meters. So that's quite a lot. It's quite an increase. Bear in mind, further down the line, this is also going to go through a final drive as well. And we will get an additional compound ratio. So if the final drive has a ratio of, say, 4 to 1, we're going to multiply it by 4 again, and so on. So you can get some really high torque values. So that's a compound gear ratio. Okay, so we now know what a gear ratio is, how we calculate it, what a compound gear ratio is. We're now going to add a little bit more into the mixture, and we're going to add this component here, which is known as a final drive, which contains the differential gears. Now if you look closely here, we have a gear, which is called a pinion gear, which meshes with this big round wheel, which is called a crown wheel. This also gives us a gear ratio. Now typically this is anywhere from 3 to 5 to 1 ratio, but the average is probably around 3.5 to 4. Now this is quite an easy component to modify. Anyone who's into motorsport might know that this is something that can be easily switched to, sometimes a little bit more easily than the actual gears in the main transmission. So just by changing this, we can vastly improve the torque output, or we can vastly improve the top speed, depending on the circumstances. So what I'm going to do here is just run through a bit more of a real world example of how the gear ratios are affected, or how they affect the speed and the torque. So these numbers here are some I've just plucked out. They're not to a specific vehicle, but they're kind of just round about what some vehicles are. Some are different, some aren't. I've also added a reverse gear in there just for example. So when we finish this, you could go through some of these numbers. You could look up the specifications for a vehicle that you like. Sometimes quite easy to find on the internet, and do some calculations yourself and see if you can work out why the manufacturer designed in these gear ratios. So what we've got first, this first number, for example, if I'm in first gear, I've got a gear ratio of 3.9 to 1. and that is already calculated for us. That is the compound gear ratio that is already worked out for us in there. Now you could take this gearbox apart, you could count the teeth if you wanted, you could work it out yourself. If you're ever taking a gearbox apart and having a look at it, it's well worth doing just so you understand what's going on in there. So these are the gear ratios. You'll notice though that the fifth gear is 0.8, so it's less than 1. That is because it is an overdrive gear. That is, the output is going to rotate faster than the input. If you have 6 gears, that will be even less. It could be 0.7 in this case. It's the only gear that does that. Fourth gear traditionally was always 1-to-1. Depends on the gearbox. For this one I've put 1.1-to-1, which is more like a front wheel drive. But the numbers aren't really that important. It's the way we calculate them. So I'm just going to put some figures down to show you how we calculate the gear ratio now and how it affects the speed at the wheels. Okay, so simply here I will put, let's change to black. So we'll have first gear, okay, and again we're going to multiply them. I'm going to treat this as a compound gear ratio. That is the differential ratio of 4.2 and the transmission ratio when the gear is selected. So it's simply going to be 3.9 multiplied by 4.2. Okay, rather than run through every single gear, I'll skip a couple of gears. So we'll look at third. So that gear ratio is 1.4 multiplied by 4.2. And we'll look at fifth. And that gear ratio is 0.8 multiplied by 4.2. Okay, now if you're good at maths, you can work those out. If you're not, don't worry, you can use a calculator. And for the first gear, you will get a huge gear ratio of 16.38. Now you can round to 16 if you want, but it does affect the accuracy of this if you wanted to know accurately what you're getting at the wheels. The third gear, I get 5.8. Let's put that there. And the fifth gear, I get 3.36. So you can see there's a big difference from first gear to fifth gear. Now first gear, those of you who drive will know that's only really used for setting off. So it doesn't serve a practical purpose after that. Now, if we put some numbers in here, so let's say our engine is rotating at 5,000 RPM. So that's like we're kind of cruising at a pretty high speed. And at that speed, it's producing a torque, and again, I'm going to keep these numbers pretty simple, of 100 Newton meters. Okay, so it's not the most powerful engine. This is probably equivalent of like a 1.6 petrol or something like that. So yeah, a 1.6 petrol doesn't produce as much torque as you think it does. The torque we get at the wheels is all to do with the gears. If we didn't have a gearbox, we wouldn't move very well. 100 Newton meters is quite low. So we want to know the speed and the torque at these points here, at the wheels. So what we're going to do with this ratio is just like we've done in the other examples. For the speed, we're going to divide it. So if we divide, and I'll write it in so we don't lose track, 5,000 divided by 16.38. So this is a good habit to get into, writing down your working. You probably got that all through school, but it does help. If you get a weird number at the end and think that doesn't look right, it probably isn't. So you can go back and find out why you got that wrong. So that'll give us a speed at the wheels of 305 RPM. This one is 5,000 divided by 5.8, and that will give us a speed at the wheels of let me just check that. Let's see, I've just done that now. I've got the wrong number written down and I've noticed it. Divided by 5.8, That's 862. So just as I was just saying then, I saw this number on my paper of 300 and something, just thought that's not right because that's first. So I've obviously squiggled it down somewhere wrong. And then the fifth gear is 5,000 divided by 3.36, and that will give us a bigger number of 1,488 RPM. So you can see there the speed increase from first gear to fifth gear, which is what we're cruising at on the freeway or the motorway, is significantly more. And that's the speed of the wheels. You could then work out things like the speed of the vehicle from the rolling radius of the tyre, but not in this video. We'll probably tackle that at a later date. So then if we look at the torque values, all I'm going to do for torque, I'll change colour again so we can see, I'm going to multiply the 100 Newton meters by that ratio. So this one is going to have a massive torque of 1,638 Newton meters. This one is going to have 580 Newton meters, and this one is going to be 336 Newton meters. So you can see why I use 100, it's just quicker to work out. So not much torque at the wheels at fifth gear, and anyone who's tried to set off from a standing start in fifth gear, the car's going to struggle. You'll probably burn your clutch, it might cut out. But 1,600, that's pretty typical for a first gear in a lot of vehicles. First gear ratio is usually around 4, we've got 3.9 in this one. So we've gone from looking at what a gear ratio is, why we need it, what it does, how we can calculate it, how that can then be combined in a compound gear set, and how we can combine it with a differential and final drive assembly to work out the speed and the torque at the wheels. So if you go away now, you could have a look at some of these other numbers, have a look at some other vehicles, and you could do your own calculations. There's plenty of calculators there on the internet if you search that people have put up. And if you're a bit nerdy like me, it's actually quite interesting. So thank you for watching. So if you subscribe to the channel so you catch any later videos, I'll be coming back to this a bit more complex at a later date. And if you want to leave any comments to discuss anything in here, please feel free below. So thank you very much and see you soon.